most of you are familiar with vectors. Just for sake of definition, we can say that vector is a quantity that is defined by a magnitude and direction. Typical vectors are velocity, displacement, force, and so forth. The difference between a scalar and vector is we can use the difference between vector velocity and speed to point out the difference between these two quantities. Okay, so is displacement and distance. I can go 1 mile in one direction and return 1 mile back, and I'll be at the same starting point. My displacement will be 0. My distance was 2 miles. So, and my velocity, whatever the average velocity that I had, you can say that the average speed was 0 because I have no displacement. So, in physics, in mechanics, and other branch of sciences, we use vectors a lot. Force is a good example. So let's write in terms of definition that a vector, a quantity, defined by a magnitude. Oops, don't know why. I'm adding letter and direction. So typical vector represent displacement, velocity, and force, to just name a few. So the keyword magnitude and direction. The notation that we use in this course, actually before we go into notation, we're going to say that a vector from AB, like so, has an initial point A and a terminal point B. Okay? So, for instance, if this is the point A and this is the point B, the way we define the vector AB is we go and we draw an arrow from the initial point A to the terminal point B. Okay? And we're going to say this is vector AB. Of course, if we go in reverse, that will be either negative AB or BA. Okay? Notice that the magnitude is usually represented by the length of the vector. So in this case, we're going to say that this vector has 1, 2, 3, 4, 5, 6 units. Okay, so the magnitude, the correct notation is to use this notation, but a lot of time in our textbook, the arrow on top is being dropped. Okay, so we'll use, in our text or in our course, we'll use just this one, and it's equal 6 units, okay? And the direction, normally the reference point will be the positive direction of the x-axis. So this is theta, so this is the magnitude, and direction is the reference angle theta, okay? In the text, a vector, all the vectors will be pretty much lowercase but bold. Here we cannot use bold when I write in the script. So I'll use the arrow symbol. Okay. So in terms of notation, I'm going to say that vector V, like so, lowercase with an arrow, will be AB. So in this way, I don't have to worry about what is the initial point and what is the terminal point. Matter of fact, it makes no difference, because if you look at two-dimensional vector, and again, most of you recall that whether you learn about vectors in trig or in pre-calculus, which was ages ago for you guys. But if you're looking at two vectors in R2, and if I'm looking at a vector that has a horizontal component that is 3 and a vertical component that is 2, this will be the vector. Okay? One way to represent this vector, if this is vector v, we're going to say that v has a horizontal component that is 3 units and a vertical component that is 2, and I'm using this notation, the triangular brackets. Okay? So in 2D, I have 2 components. 3D, I'll have 3 components. Okay? So now V, I'm sorry? Oh, it's somebody outside? Okay. Sorry, cannot answer. Now, the thing is this. I can, the same vector V can be moved and remain the same. And that's one of the properties of the vectors. Vectors are independent of their corresponding initial points. So the vector that is denoted as 3, 2, I can put it right there where I have x equals negative 2, x equals 2 and y equals negative 2, and go 3 forward and 2 upward, and the same vector, vector v, will be placed right here. Okay? These two are identical. Why they're identical? Because this one has a component 3, 2, and this one has component 3, 2. Okay? So vectors are independent of their initial points. Let's write. So if I write v1 and v2, and then note v1 equals v2, and both of them equal v. Okay. Vectors are independent of their initial points. So you can move, and we will move the vectors either on a plane, on xy plane, or in space, and it is going to be the same quantity, because the magnitude and direction remain the same. Right? Just to demonstrate, if I pull up a chair on the wheel, like so, and I push in a certain direction by a certain force, right? So I apply a force that is a vector. Now it doesn't matter if the chair is here and I push it. As long as I push it in the same direction with the same magnitude, I apply the same vector, the same force vector. So that's the practical meaning of independence of this statement, where we say that vectors are independent of the initial point. Another important notation, which will kind of simplify the representation of a vector, is using standard unit vectors. Okay, so we'll define standard unit vectors those will be vectors that have a length of 1, a magnitude of 1, and they're pointing in the x direction or the y direction, and if we are doing with R3, in the z direction. So I'll define those vectors in both universes. So in R2, okay, we'll define vector I, again, if in print it will be bold, but here I'm going to initially mark it with the arrow, but later on I'm going to drop it. It's a vector in R2 that has a component 1 in the x direction and component 0 in the y direction. And J, likewise, but has a 0 x component and 1 y component. Okay? In R3, we'll have I that has 1, 0, 0. In other words, it has one unit in one length of 1 in the x direction and nothing in the y or z direction. J will be likewise will be 0, 1, 0, only y component, and k, unit vector k, all lowercase by the way, will be 0, 0, 1, like so. Okay. So if you imagine what is ijk, if I'll draw a three-dimensional coordinate system, like so, with x, y, z, and I'll do it 3 times, and let's see if I can use color to demonstrate each one of the unit vectors, the standard unit vectors. I think the book has slightly different name for that, but I'll go along with the name that I have. So I will be this vector, okay? J will be this vector, and K will be this vector. All has length of 1. Okay, so